Let's continue to block diagrams and signal flow graphs. In this chapter, we introduce block diagrams as graphical alternatives for modeling control system and their underlying mathematics. Block diagrams are very popular in the study of control system because they provide better understanding of the composition and interconnection of the components of a dynamic system. A signal flow graph may also be used as an alternative graphical representation. Let's start block diagrams now. As we learned at the last lecture, in here we have an example for a control system. We have input as desired room temperature and thermostat to measure the room temperature. In here we have another signal which is feedback from the output of the system, as you see. And at this point we have error voltage and after that gas valve to control the temperature and then furnace to heat the system. We have a comparator here. Heat loss may be, for example, in the room, a window. If you open the window, this is a heat loss for the room temperature. And then we have a plant which is in room. Okay, so it is a simple example for the control system. Room means in the control theory in general plant. Heat loss can be set disturbance for the control. Actual room temperature output for the system. Furnace, actuator. Actually both of them are actuator for this system. In here we have a sensor. It can be here and here also. At this point we have input signal and at this point we have feedback signal. It is important to say that for nonlinear system we can use also block diagram, but in the nonlinear system we use time domain equation. If you use block diagram for the linear system, we will use Laplace transform variables. Okay, modeling the typical elements of block diagrams in control system, we have some components for the block diagrams. Comparators, we will see all of them in detail. Block representing individual component transfer functions, reference sensor, output sensor, actuator, controller and plant. So the general representation of a system block diagram can be used as like that: input signal, reference sensor, output feedback through the output sensor, as you see here. We have a controller and then actuator to control the system. We may have disturbance, external disturbance also. We have another comparator here and plant, which is to be controlled. Let's start from comparators. Comparators, as you understand from the name, comparators compare the two or more than signal. For example, in A, RS minus YS, Y minus, as you see here, the second signal is minus. So the error signal will be RS minus YS. In B, as you see, we have plus sign. So it means the error signal will be RS plus YS. Also, we may have more than two input for the comparators, as in C, R1S plus R2S minus YS. What about the blocks? Blocks represent the equation of the system in time domain or the transfer function. As you see in this figure 4.4, you can use the time domain or Laplace transform. But as I said before, we use time domain function for the nonlinear system, but for the linear system we always use the Laplace domain equation as you see in this block GS. What we have for this kind of system, what can we define the output and input relation? XS divided by US is equal to GS. Okay. For example, we have an example here. We have two transfer function or mathematical equation or Laplace transform, G1s and G2s. Okay, what is the AS here? AS will be US times G1s. What about XS? XS will be G2s times AS. So when you put AS into the second equation, you will get G1s, G2s, and US. So we can get the output and input relation as G1s times G2s. This kind of system called as cascade. Okay, cascade. These two blocks connected in series. So this kind of system called as cascade system. We have another example here. As you see, again we have two blocks, G1s and G2s, and connected in parallel. How can we get the input-output relation again? We can write A2s as US times G1s, and for the A3s we can write US times G2s. So XS will be US times G1s plus G2s. The input-output relation of this system can be given as G1s plus G2s. This kind of system connected in parallel. Yes, let's continue. What about the feedback? Okay, for a system to be classified as a feedback control system, it is necessary that the controlled variable be fed back and compared with the reference input, as you see here. The output signal is feedback from a sensor here, as you see, to the input of the system. So how can we get the input-output relation again? US will be RS minus BS. What is BS? BS is equal to HS times YS. So we can write this equation into the first equation. YS will be equal to US times GS. So we can write US as RS minus BS. YS will be RS minus BS times with GS. And again, for the BS, we can write the second equation. YS will be equal to RS times GS minus GS, HS, and YS. If you arrange this equation according to the YS, you will get the YS over RS as GS divided by 1 plus GS HS. If the feedback signal is positive, as you see here, for the feedback signal we will use negative here. If it is positive, so this signal will be negative. Okay, but if it is negative, we can get positive, as in you see. Okay, relation between mathematical equation and block. This is the second order prototype system, as you see here. This differential equation belongs to the second order prototype system. If you assuming zero initial condition, it means x0 and derivative of x0 will be 0. So you can get this equation. And if you arrange according to the higher order xs, you will get the last equation. So, how can we get the block diagram for this system? As you see, s square xs is equal to omega n square us, this term, plus, minus the second term, 2 xc omega n square xs, and minus omega n square xs. Maybe we can arrange this figure as like that. If you get the output of the system xs, maybe it can be changed. In here we used a block and it includes the 1 over s square. Okay, so it means in this point we have s square xs. So if you know this, we can write input as again omega n square us. What about the other terms? At this point we have xs, so this block will be 2 xc omega ns. Where is it? In here. What about the last one? It will be omega n square. Maybe we can arrange some more. Let's do it. If you get omega n square after the input, you can write this figure as like that. And also for this block, we can use two cascade block, 1 over s and 1 over s. The output will be xs again, but we know this now. In here we have s square xs, and at this point we have s xs. So how can we arrange now? As you see here, in this block we have an s term, but now we don't need to use s in the block if you get this signal from at this point. As you see here, we get this signal at this point, and after that 2 xc omega n, and also from the output omega n square, we use the feedback. Example, let's get the transfer function of the system given in this block diagram. How can we get it? To represent the system as like that, what can we do now? As you see before, we have an omega n square term and also the same term in here, omega n square. So if you write this term after the comparator, we can get the feedback as unity feedback. What about the others? In here again, we have s xs, and at this point we have s square xs. So we can get the s xs for the 2 xc omega n. Now, as you see here, we have an inner loop in here. What is the transfer function with respect to the inner loop? We can write directly Vs divided by A1s will be equal to 1 over s divided by 1 plus 2 xc omega n over s. So it will be 1 over s plus 2 xc omega n. So we can write for this part this equation. Now, as you see here, in here we have omega n square if you eliminate this, and also 1 over s plus 2 xc omega n, and after that we have another 1 over s. What about the other, this part? What can you say? Cascade system. they are connected in series. So we can say directly omega n square divided by s square plus 2 xi omega n s for this part. What about the total system? The outer loop. What can we say? This is the closed loop system, and we can write the xs over us as omega n square divided by s square 2 xi omega n s and divided by 1 plus omega n square divided by s square 2 xi omega n s. If you arrange this equation, you will get omega n square divided by s square 2 xi omega n s plus omega n square. This is the transfer function for this system. By using the block diagram, you can get also transfer function as like that. So you have to do some manipulation on the block diagram. This is the closed loop transfer function. We can also represent this system with another way. In this system, this block can be called as open loop transfer function. The total system can be said closed loop transfer function. Let's consider this system. At this point we have ES. Suppose that. What is ES? ES will be RS minus YS. What is YS? YS is equal to ES times GS. If you write this equation into here, it will be RS GS minus GS YS. Okay. If you get YS, 1 plus GS, which is equal to RS times GS. So the input-output relation can be given as YS over RS, which is input for the system, GS over 1 plus GS. If you want to get VS over US at this system, where is it? For this system, we want to get VS over US. What should we do now? Maybe we can draw the same system again. US. Until now we know a comparator omega n square over S plus 2 xi omega n. At this point we have Vs, and what about 1 over S? It can be feedback according to the Vs, as you see. So in this diagram, if you get Vs and Us, you can find the relation between the Vs and Us, which is Vs over Us will be omega n square divided by S plus 2 xi omega n divided by 1 plus omega n square S plus 2 xi omega n times 1 over S for this system. So finally you will get S omega n square divided by S square plus 2 xi omega ns plus omega n square. According to the last relation, xs over us, we have also s here, which comes from the 1 over s. As you see in the diagram, Vs will be s xs.